Ladies and gentlemen, good afternoon. The presentation I will talk about is locomotive wheel-wear simulation in complex environment of wheel-rail interface. The outline of my presentation consists of 4 parts, including background, modeling, results, and conclusions. First of all, I will briefly introduce the research background. Generally, the X-load of locomotive reaches 25 tons or even 30 tons. The wheels need to support the locomotive's wheels, but also need to transmit the traction and braking forces to the rail. Moreover, the wheel-rail interface is an open system. For example, water, oil, or other third body could present at a wheel-rail interface. These factors make the service environment of locomotive wheels quite complicated and wheel wear more severe. An online wheel wear prediction model taking into account the track flexibility has been proposed in our previous paper. The wheel wear prediction model is put forward recently. It consists of 3 parts: the locomotive track coupled dynamics model, the creep control model, and a model for wear estimation. Each part of the model will be introduced next. The first sub-model is locomotive track coupled dynamics model, which is built based on this model. The model consists of a locomotive, track, and wheel-rail contact. The bogie is provided with 2 states of suspensions. 3-dimensional spring dimple elements are employed to represent the primary and secondary suspensions. The ballast track is modeled, taking into account the track flexibility. The rails are modeled with team single beams discretely supported by the slips. Each slip is assumed as a lamp mass. The lateral, vertical, and roll motion are taken into account. The ballast bed is treated as equivalent rigid ballast body. Only the vertical motion is considered. The track and the locomotive and the track model is coupled with the wheel-rail contact relationship. The contact position is determined based on traction line method. The nonlinear Hertz elastic contact theory is used to calculate the normal contact forces. The tangential contact is slowed by the modified fast seam proposed by Spoyagin. Not only the global creep forces, but also the local creep distribution and the tangential stress can be obtained, which are necessary for wear estimation with the local wear prediction model. Typical model parameters for dry and wet conditions of Planck's model are available in reference 22 in this paper and listed in table 1. The model parameters of the modified fast seam can be identified by comprehension with the calculation results of Planck's model. The identified model parameters are shown in table 2. The second sub-model is the creep control model. A simple creep control model named PI control is used in this paper. The driver nodes and the creep control threshold value are pre-established. The locomotive speed and the wheel set speed are collected in every time step, which are used to estimate the actual creep. If the actual creep exceeds the creep control threshold value, the traction or braking torque is will compensate according to the proportional integral equation until the actual creep less than the creep control value. This third submodel is wear calculation model. The view wear in dry condition is calculated by using the USFD wear function developed by the University of Sheffield. However, the view wear in wet condition is calculated by using the wear function developed by Southwest Jiaotong University, which can be found in reference 29 in this paper. The two wear functions are T-gamma model. After introduction the simulation model, let's move to the third part. Some simulation results are presented. First of all, the locomotive track coupled dynamics model is validated. The input information is shown in the left figure. The speed, traction, and braking force are obtained from the monitor data of locomotive. The traction or braking torque is applied to the wheel set. Other external force is applied at the end of locomotive at buffer height. The speed of calculated is consistent with the monitor data as shown in the right figure. Moreover, the dynamics performance of the locomotive is validated in our previous paper published in multi-body system dynamics. Traction and braking have a great influence on creepages and creep forces. The effects of traction on wheel wear were investigated firstly. The simulation is performed on straight track. The wheel rail interface is summed as dry condition. The wheel wear simulation is performed when the locomotive is accelerating from 10 to 80 km per hour. The drive load is set to the highest level. As a comparison, the wheel wear in without traction case is also investigated. The traction torque is applied at the wheel set for the traction case. However, the total traction force is applied at the gravity center of the car body for the without traction case. The speed of the locomotive is the same for the two cases. The wear distribution is shown in the left figure. It is similar for the two cases, but the wear depth in traction condition is about twice as much as that without traction. The wear error is shown in the right figure. The differences between each wheel set is quite small, but the wear error in traction condition is about 1.6 times larger than that without traction. The effects of braking on wheel wear is also simulated during the locomotive decelerating from 80 to 10 km per hour. The simulation results show that the wear error is about 1.3 times larger than that without braking. These results indicate that traction and braking cannot be neglected for locomotives wheel wear simulation. Otherwise, the wheel wear will be significantly underestimated. The effects of braking on wheel wear is also simulated on curved track. A visual track is designed for this study. All the curves are assumed as left-hand curve. The wear distribution of the first bogie is given. It is similar for the two cases, but the wear mount in braking condition is much higher than that without braking. There are two peaks for the first wheel set. One peak is found on curved tracks with radius less than 1,000 meters, and the other is found on the curves with radius equal to 2,000 meters on a straight track. However, there is only one peak at the central part for the training wheel set. they same as the straight track. They same as the straight track case. The wheel error in braking condition is about 1.3 times larger than that without braking. The effects of creep control on wheel wear is also investigated in vert condition. The left two figures show the longitudinal creep pitch of the first and the fourth wheel set. For the first wheel set, the longitudinal creep pace varies around the creep control value. For the fourth wheel set, the maximum adherent force will larger than the traction force. When the locomotive speed reaches a certain value, the actual creep decreases. The creep control will not be triggered. When the creep threshold value exceeds the saturation point, stick slip vibration could present. The simulation results with the creep threshold value of 0.08 show that the wheel set reference in longitudinal direction is excited by the stick slip vibration. The dominating frequency is about 24.5 Hertz. The wheel wear simulation results show that the wheel wear increases linearly with the creep control value. It is a better way to control creep value by using a variable control model related to the locomotive speed, which cannot guarantee the exaction of traction force, but also can ensure wheel wear in a low level. Last, we will draw some conclusions. First, a locomotive wheel wear simulation model is developed, which includes locomotive track curve dynamics model, creep control model, and the wheel wear model. Secondly, the traction and braking have a great influence on wheel wear, which should be taken into account for locomotive wheel wear simulation. The wheel wear will be underestimated if the traction and braking are negative. Lastly, the wheel wear increases linearly with the creep threshold value. It is a bad way to control the creep by using a variable creep threshold control model related to locomotive speed. That's all. Thank you for your attention.
Okay, thank you.